Greetings everyone, this is Kurala Mudan and I'm a second year student from VIT Chennai and I'm here to explain and demonstrate the NAND2TETRIS Project 1 and 2, the journey of building a novice from a NAND gate. NAND2TETRIS is a course in fundamental computer engineering that steps you through the creation of a computer from a simple NAND gate. So what we are going to do here is we are going to build a computer architecture just using a NAND gate. Like not exactly using a NAND gate, but we are going to use the NAND gate to make some logical gates, and with those logical gates we are going to build much more logical advanced logical units, and with those we are going to build architecture, machine language, assembler, and then we are going to load an operating system on it, and over the operating system we are going to test some simple programs like Tetris. So we are going to build a prototype computer called a hack, only using the NAND gates as a basic universal gates. So let's head on. There are 12 chapters in this course, and each of which will tackle a next logical step in building the computer called hack. So at the end of 12th chapter, we'll have with ourselves a computer called hack, which will be capable enough to run a program like Tetris. So these are the 12 projects that comes in hand when we are doing this course. So starting from Boolean logic, Boolean arithmetic, sequential logic, and go on, we have the operating system. And at the end of the 12th project, we'll be running a small Tetris game on our computer. So in this demonstration, we'll be looking keenly into the Boolean logic and Boolean arithmetics. So in the first project, we'll be setting up all the required logical gates only using the NAND gates. And in the second project, we'll use those logical gates to build advanced logical units, a bit more advanced logical units. So how are we going to do this? How are we going to build our prototype computer called hack? Are we going to bring on some NAND chips and connect them together? No, we are going to do it virtually. So we are going to use a software where we can actually create and design different chips, different logics, and then we can assemble them together, run them, and do all the testing is within the software. So what is the software that we are going to use? For this, NAND2TETRIS have officially released a software suite which we'll be looking on right now. So this is the NAND2TETRIS official software suite, and we get two folders into this. We get a project folder which has 14 different projects numbered from 0 to 13 and a demo. And for this demonstration, we'll be only looking to project 1 and 2. So here is project 1. We see a bunch of files over here, and we see something common. We see something familiar. That's the logical gates. We have AND, we have demux, we have mux, we have not, we have nor, or. Okay, so these all we know. But there's something a little strange here, that we have each gate 3 times, which means that we have 3 extensions for each gate, which is CMP file, HDL file, and TST file. So we'll be looking onto it right now. So let me go to the tools section. In tools section, we again have a bunch of files, but all of these are Windows batch files. And these are all the tools that we are going to be needing to run the different projects. So here we have the tools like assembler, CPU emulator, hardware simulator, JAK compiler, text compiler, and VM emulator. So in the first 2 projects, we are basically going to be building hardware units like gates, different logical units. So for our project 1 and 2, we'll only be using the tool called hardware simulator. Let me open that up. Yeah, so this is the hardware simulator. This needs Java runtime environment to run. As I already have it, I'm not installing in front of you again. So we see lot many windows in this software. We have input pins, output pins, HDL. HDL stands for hardware description language, and it is used to code the chips and to define how it works. And we have some icons over here. We have an icon to load a chip, to run the program, to load script, and we'll be looking on to this again later. So let's go on with the presentation. So we come to the project 1, that is Boolean logic. We'll be creating the following list of logical gates and using NAND gates. We are only going to use NAND gates. We are not going to use any other gates to make all these logical gates. So let's get on. So we have different logical gates like AND, OR, NOT, XOR. So all the possible logical gates we are going to be trying to build only using the NAND gate. As we know, NAND gate is a universal gate with which we can build almost anything. Come on, let's go. So first we'll be looking at the AND gate. So we know that AND gate can be made using 2 NAND gates. Basically, we'll be supplying the 2 inputs to the first NAND gate, and we'll be routing an output which is going to be A.B under bar. And then we're going to be supplying it to the second NAND gate. We're going to share A.B inverse identically to the second NAND gate, and it is going to produce an output of A.B inverse whole inverse. So the inverse and inverse are going to get cancelled, and we are going to have A dot B at the output. So let's check that out. So we open the hardware simulator over here, and then we go for the AND.hdl. So we are going to load the hardware description language. So we have loaded the chip, and now we can see that it has input A, B, two input variables and one output variable. So we have two NAND gates over here. So one NAND gate is going to take the input of A and B and produce an output called NAND AB. And then the next NAND gate is going to take the identical input to both of its input lines, like A is NAND AB and B is NAND AB, and the out is going to be out. So what the second NAND gate produces is the out that we are desiring, that is the AND out. So let's load the script and.txt, and let's try running it. So once this yellow line reaches the end of the page, it means that we have done compiling and we are ready to view the output. So here we go to the view panel and we select output. So here we can see that the truth table and the truth table in the presentation are matching. And here we can compare and see if we are right. But there is another way how we can do this. Here we can also hit the compare button to show the expected truth table that is desirable for the chip that we are designing. So since the expected truth table and our truth table are matching, we don't see any difference. So the output and the compare are same. Okay, so let's head on with the next logical gate, that is the OR gate. OR gate a bit more complex compared to the AND gate because it needs three NAND gates. So what we are going to do is we are individually going to inverse each of the input, and then we are going to supply it to the third NAND gate. So here we get the A bar, and here we get the B bar, and we are going to supply A bar and B bar to the next NAND gate. So the produced output will be A bar dot B bar whole bar. So when we apply De Morgan's law, the bar becomes cancelled out and the sign changes. The Chinese sign inverses between the A and B. So it becomes A plus B. So this is the truth table, and let's head on to the hardware simulator and try running it. We're going to select or.hdl. I'm sorry, or.hdl, and we're going to load that, and we're going to load the script for or. Okay, so as we can see here, there are three NAND gates. A is equal to A, so there are two identical inputs and two identical inputs. We are individually inversing both of the inputs, and then at the third NAND gate we are going to supply not A and not B and take the out. So let's try running it. So we have done compiling it, and now see, yeah, so we get the exact same truth table. So the output is high only when when any one of the input is high, either it is A or B or both A, B, the output will be high. Only in the case when both are low, the output will be low. So let's get on with the next logical gate, that's the NOT gate. We discussed the NOT gate when we were handling the AND gate, because in the AND operation we were actually NOTing with the second NAND gate. So here it's the same. We have one input and one output. So the output is always going to be the inverse of the input. So we are going to share the input in both of the input lines of the NAND gate, and we are going to derive the output at the other end, because A dot A is going to be A. So A dot A whole bar is going to be A bar. So that's how it works. Let's again try it in the hardware simulator. We'll load the chip for not.hdl, and we'll also load the script for not.tst. Yeah, so we see here there is one input and there is one output variable. So there is only one NAND gate involved, and the input is going to be symmetric to both the input lines, and the output is going to be derived with that. So let's go ahead and run this thing. And now we see that we got the expected output. For 0 it's 1, for 1 it's 0. Let's go on with the presentation. We have the exclusive OR gate. This exclusive OR gate, it's like the exclusive OR. Like it's like OR, but it doesn't work when both of its inputs are high. It doesn't produce a high output when both of the inputs are high. It only produces a high input when only one of its output is high. So when both the outputs are low, it is not going to produce. When both the outputs are 1, it is not going to produce. So it basically means that when both the inputs are identical, it will produce a low signal. When both the outputs are non-identical, it will produce high signal. So this is the implementation of an XOR gate. Let's now check out how it works in our hardware simulator. XOR.hdl, XOR.txt. Yes, so we have four NAND gates, and let's try running it. So this is the exact, this is exactly implemented how the pin diagram here shows. We have four NAND gates, and the logic is also shown here. So let's go on and try the output. So as we can see, for both 1 it is 0, for both 0 it is 1, for 1 and 0 it's 1, and 0 and 1 it's 1. So we got the desired output. I skipped a lot. Yeah, here we go. It is a multiplexer. A multiplexer is a bit different than the other logical gates that we saw right now, because multiplexer has two types of inputs. There's the data input and there's a select input. The data inputs are the stream of data which are coming inside to the multiplexer, and the select lines are to select which data is to be forwarded to the output line. So if there are if there are data inputs that come under the range of 2 power n minus 1 to 2 power n, there should be n select lines. If there are 3 data inputs, there should be 2 select lines. Even if there are 4 data inputs, there should be 2 select lines, because 2 power 2 is 4 and 2 power 1 is 2. So the 3 is between 2 and 4, so you need 2 select lines. So it works in that way. So if the select lines produce selection of 0 and 0, then the zeroth input, that is the A input, is going to be forwarded to the output. No matter if the input is A, so if the input is 0 or 1 in A, even if it is 0, it is going to be output as 0. Even if it is 1, it is going to be output as 1. So whatever it is in the data line, it is going to be forwarded to the output line. So let's check out with our hardware simulator. Let's check the mux.hdl and the mux.tst. Here we are going to see a two-way multiplexer. So here we have only two input data lines and one select line. So when there is 2 power 1, that is 2, so we only need one select line. So here is the implementation, and let's run this. Yes, so output. So here we have two input data lines and one select line. So when the select line is 0, it will select the data of A and give it to the output, so it is also 0. In this case, we can see that the select line is 1, so it will take the data of B, and since B is 1, the output is shown as 1. And here, since select line is 0, it will take the output of A. A is 1, so the output will be 1. So it works in that way. Now, demultiplexer is the exact opposite of multiplexer. So we saw that the multiplexer takes a parallel input, and it serially gives out only one of the parallel input. But here in demultiplexer, it takes one input, and according to the select lines, it channelizes the output. Like, it will take the input of F, and according to the selection lines, it will decide whether to channel the input line F on either channel A or channel B or channel C or channel D. So according to the select lines, it will forward the F to either A or B or C or D. So let's see how that works in our hardware simulator. We have dmux.hdl and we have dmux.txt. In this, again, we have only one input, one data input and one select line, and we have two output lines. So this is a two-way demux. So here, let's check out the output so that I can explain it properly. So this is one input line, and this is a select line. So when select is 0, it will going to select the output channel of A, and it is going to forward the input line to the A output line. So here we can see that the select is 0, so it will choose A as the output line. So since the data in the data line is 1, it will give the output as 1 in A channel, while the B remains 0. So it means that the demultiplexer is working perfectly. So let's go to the 16-bit variants. Okay, so since all the variants that we saw in AND or MUX and or NOT, it were single-bit variant. So there was only one bit in the data line, and only one bit was forwarded out at the output line. But here we are going to do the same, but we are going to have 16 bits of data in each input. So if you see that there is AND 16-bit or 16-bit, multiplexer 16-bit, and not 16-bit. So in AND 16-bit, there are going to be the AND operation performed between 16 bits of data. So here we can see an example. There is an A and B, which are 16-bit data. So here the AND is going to be performed between each single pair of bits. So in this, first bit of A and first bit of B are going to carry on a AND operation. So 1 and 0 is 0. 0 and 0 is 0. 1 and 1 is 1. And the output is again going to be generated in 16 bits. So let's go ahead and check one of some of the 16-bit variants of the logical gates described here. Let's go to and16.hdl, and then let's go select and16.txt. So as we can see here, we have an array of input lines. So A is an input, and A has 16-bit input, and B is an input of 16 bits, and out is an output, a variable of 16 bits. So we are going to have 16 NAND gates, 16 AND gates. So we know that for one AND gate we need two NAND gates. So for every AND gate implementation, we are going to use two NAND gates. So for every bit there is going to be two NAND gates. So since we are dealing with 16 bits, there is going to be 32 NAND gates involved in this chip. So we can see this is for bit 1, this is for bit 2, this is for bit 3, this is for bit 4, and similarly till bit 16 there will be two NAND gates for each operation. So let's try and run. We are going to give some test cases, and the test cases and its equivalent output are going to be displayed at the display output view. Let's see the output. So here we can see that the 0000, so when we AND each of the corresponding bits, the output is going to be 0000. Now here if we see there is 1111, so the output is going to be 1111. So we understand how it works. Then we are going to look at the OR 16-bit OR function. So similarly, there are going to be 16 OR operations carrying out simultaneously. So each bit is going to be ORed with the corresponding bit of the other input line, and the output is going to be decided by the OR operations. So we know that for carrying out an OR operation, we need 3 NAND gates. So for each bit, there are going to be 3 NAND gates. So all these 3 produce the output for bit 1. All these 3 are for bit 2. For these are for bit 3. So in total, we are going to need 48 NAND gates to implement this chip. So let's go on and check it. We again give some input test cases, and let's see what are the outputs. Yeah, so again we see that 00001111, we produce an output of 1111. For 10101001, we also produce 111, because either one of the input should be high at bit level. So let's go to multiplexer 16-bit. So this is going to be a normal two-way multiplexer, but there is going to be 16 bits. Since we already did a multiplexer chip, we are going to use that chip alone to do this. So we are going to need 16 multiplexers to do this. So let's also take these multiplexer 16.txt and let's run. So we need 16 1-bit multiplexers to make a 16-bit multiplexer, because this is going to do the job 16 times. So let's look at the output. Yeah, even the output is going to be correct. There's 2 inputs with 16-bit input lines, and 1 select, because there are only 2 sets of input. Now let's go on to not 16-bit. Yes, again, we only need one AND gate for implementation of one NOT gate. So only we are going to need 16 AND gates to make this chip. So each NAND gate is going to inverse the output of each bit, and it is going to produce an array of 16 output lines. Let's run this. Again, we feed in some test cases on the script viewer. Yeah, now output. We see that for 1111 it's 000, for 1010 it's 0101, for 0011 it's 1100. So we conclude that this is doing out right. Now let's move on with the presentation. So there are multi-way variants. Okay, so here we'll see an n-way gate has n inputs to produce the output. So if we take a look at the multiplexer, we have 4-way multiplexer. So we saw that we had 2-way multiplexer when we tried it out demonstrated in the hardware simulator. But here there is 4-way multiplexer. So what it means is there are 4 inputs, there are 4 data lines of each 16-bit. And if there are 4, 2 power 2 is 4. So there needs to be 2 select lines. So here we can see that there are 2 select lines to select between the data input lines. So Similar way, there is going to be 8 inputs in for OR 8 way. There are going to be 4 inputs for MUX 4 way. For MUX 8 way, there are going to be 8 inputs. If there are 8 inputs, there needs to be 3 select lines. So similar way, 8 the N way means there are going to be N inputs, N distinct inputs. So if you see, M-way n bits means an M-way n bit multiplexer selects one of the M n bit inputs and outputs into one n bit output line. So there are going to be there are going to be M inputs of each n bit. So all the bits are going to be n bits, all the input lines are going to be n bits, but there are going to be M input lines. And there is only going to be one output line, but it is going to be of n bits. So let's check out the following chips in hardware simulator. Yes. So let's check out OR 8-way. So there are going to be 8 inputs. There are going to be 8 inputs, and the 8 inputs are going to be OR together. So we see that there are 8 inputs. So in is a array of 8, but there is only going to be one output. There is only going to be one bit output. Let's load the script. Let's run. So there are going to be 8 different output of 1 bit each, and the chip is going to perform OR between all the 8 inputs, and even if one input is high, then it is going to produce a 1 bit output of high. Even if all the inputs are low, then it is going to produce a 1 bit output of low. Now let's check the output screen. So see, there are 8 bits. For 8 0 bits, the output is 0. Even if there is one a high bit, it is going to produce a result of high. So let's check the other chips too quickly. MUX 16 4-way. Load script for MUX 16 4-way. Yeah, so here we have 4 input data lines, each of 16 bit wide, and one output line which is going to be again 16 bit wide. So there are going to be 2 select lines, and we'll check it out anyway. There are going to be 2 select lines, and if the select line is going to produce 0, and it is going to select the first input line to forward it to the output. If it's the select line is going to represent 1, then it is going to be second input line. If it's 2, then it's third input line. If it's 3, it's fourth input line. So let's go on and check the output. Yeah. So here we can see that there are 4 input lines A, B, C, D, and unfortunately I'm not able to scroll it there. So according to the select line, the input in the select line is only going to be an input of 2 bits. So it is going to select if it's A or B or C or D, and it is going to forward it to the output line. So all the 16 bits are going to go to the output line. So now let's go on see MUX 8-way. So it's going to be 8 input MUX of each 16 bits. So we see that there are 8 inputs. From A to H, there are 8 inputs, and each input is an array of 16 bits. And we need 3 select lines, because we know that 2 power 3 is 8. Since there are 8 inputs, we need log 8 base 2 select lines. So here we are using MUX 4-way 16 to implement this. We keep 2 MUX 4-way 16, and then we interface it with the single 2-way MUX 16, and we make it as 8-way MUX. So first we are going to have a 2-way MUX here, and from that 2-way MUX we are going to give the input of one 4-way MUX and another 4-way MUX, and then we are going to select the input lines that A, B, and C, and these 3 input lines are going to produce the output, and the third 2-way MUX. So let's load the script file and let's run it. Yeah, so we are ready to see the output. So we again see that there are 8 inputs. There are 8 A, B, C, D, E, F, G, H, and then there are 3 select lines, and then there is our output line. So the 3 select lines selects which input line to be forwarded to the output line, and that particular input line is forwarded to the output line, and the 16 bits of the input line are produced as an output. Now let's head on to the demux 4-way. Here it is going to be the same. There is going to be one input, but there are going to be four output channels. So according to the two select lines over here, you can see that there is one input and 2-bit select lines, and there are four channels of output. So here we are going to do is, what we are going to do is, we are going to take one input channel and we are going to check the select lines, and with the number corresponding, like what the select lines correspond, we go to the corresponding data line and we forward the input to that particular output data line. So we're going to take one input and we are going to channelize into either of the four outputs. So let's run this. And this is a single bit mux, single bit 4-way mux. So there's only going to be one bit. There are not going to be 16 bits. Here we also do this with the help of demux that we created already, a 2-way demux. Let's look at the output. So here we see that the input is 0, 0, 1, 1, 1, and the select lines are 2. Because there are four output data lines, so we need 2 bits to select the data lines. So we see here how it works. It is actually correct. Now look at 8-way demux. So it is the similar like 2-way or 4-way demux, but we need 4-way demux to make, okay, I selected mux. We need 4-way demux to get an 8-way demux, just identical to how we created our 8-way mux. So here there is one input and 3 select lines to select between the 8 different output channels, ranging from A to H, and it's the same way. Yes, so we can look at the output. Yeah, so we see here that there is one input and there is one select line, but this select line is going to select between all the different A, B, C, D, E, F, G, H. So here we can see that if the select line is going to be 001, then it is going to go to B 002, 010, corresponding to all the 3 bits. It's going to select between which data output line to be selected, and the input is forwarded to the that particular output line. So let's head on with our project. So this was all about project 1. So let me continue my project 2 in quite a while. In project 1, we built a lot of logical gates using only the NAND gate. And in project 2, we are going to use those logical gates to build more advanced logical units, which ultimately is going to lead us to the creation of the ALU. So let's get started. In project 2, we'll be creating the following list of logical units using the logical gates we built in project 1. So with the logical gates that we built in project 1, we are going to use those and make the half adder. And with half adder, we are going to make a full adder. And using full adder, we are going to make a 16-bit adder. And using the 16-bit adder, we are going to make a 16-bit incrementer. And with all of these chips together, we are going to create the ALU. Now, ALU is going to be one of the most crucial component of our computer hack. So let's get started with half adder. So this is the pin diagram of half adder, and here I have designed the half adder only using the NAND gates. So what the half adder basically does is it adds the two binary numbers. So it takes 2-bit input and then it performs addition between them and it produces the sum and the carry. So here we see that 0 plus 0 becomes 0 and 0 plus 1 is 1, 1 plus 0 is 1, but 1 plus 1 gives you sum of 0, but it has a carry of 1. So that's why we have two output lines, which is sum and carry. So let's go and we can these are the boolean expression for the sum and carry. Here sum is a inverse b plus ab inverse, which is equivalent to a XOR b, and the carry is a dot b, which is a and b. So let's go ahead to the hardware simulator and let's run this thing. So let's load the chip for half adder and then load the script for half adder. And as we can see here, we'll see the code for half adder. So here the code for half adder, we have two inputs and we have two outputs, sum and carry. And in the parts, as I said you, for the sum, we only XOR the A and B and produce a sum. And for the carry, we just add A and B and produce the carry. So let's check out, let's run this and let's see how it works. So the compilation has been done and the output we see is desirable. So this is exactly matching with what we saw in the presentation. We can also compare it using this. So we are done. And let's head on to full adder. So here, this is a full adder implementation using only the NAND gates, but we know that full adder can also be implemented using half adders. So we can take two half adders, we can supply the A and B to the first half adder and supply the output of first half adder to the second half adder, and in second input terminal of the second half adder we can supply the C input, and then we can perform the OR and XOR and get the sum and carry. So here we can see that the Boolean expression for sum is A XOR B XOR C in, and the Boolean expression for C out is AB plus BC plus AC. Here we have three inputs, that is A and B and the carry in. This carry in comes from the previous calculation. So previous calculation, there must be some carry that has been produced. So that carry we add here and we do the addition of 3 bits. So here it is just an addition, binary addition of 3 bits to produce a sum and a carry. So here we see that this is a peculiar case where the A is 1, B is 1 and also the carry in is 1. Then the sum is going to be 1 and also the carry is going to be 1. So let's get on to the code and let's see the code for full adder. So we have 3 inputs, that is A, B, C, and we have 2 outputs. As I told you, the first half adder is going to have A and B as the inputs. The second half adder is going to have the output of A, the output sum of A and C as the input, and the OR is going to be done between the half carry and the second half carry. So let's go on to the hardware simulator and let's try this out. So we are going to see the full adder and we are going to load the script for full adder. Now let's run. Yes, compilation has been done and the output. So we have A, B and carry in, and here we have sum and carry out. So we see that this and the comparison are matching. So this is the expected output that we got. Okay, now heading on to 16-bit adder. So we discussed how a full adder works. It basically does the addition of two numbers with including the carry from the previous calculation. So here in 16-bit adder, we are going to add a 16-bit number with a 16-bit number. There is going to be an input A and B, both of 16 bits, and we are going to produce a sum and a carry, both of 16 bits. So this is the pin diagram for how a 16-bit adder will look like. We'll have 16 full adders. So we'll individually add 0th bit of A and 0th bit of B, first bit of A and first bit of B, second bit of A and second bit of B together, and then we'll compute sum 0, sum 1, sum 2, sum 3, sum 4, and then finally give the sum out and also the carry out. So let's see how it works. Let's add the chip add 16, which is the adder 16, and let's add the text file and let's look out the code for 16 adder. So as we can see, we have 16 full adders and a half adder for the first two numbers, and here also we can see that for the 16-bit adder, the C in is going to be 1. Like there's only one C in, and for the other adders, for the other full adders, this the previous full adders carry out bit is going to be the input carry for the second full adder, and for the third full adder, the carry in is going to be the carry out of second full adder. So in that manner, we actually calculate the carries of each and every addition, and finally we give a carry out. So the first design, in the design, first adder is going to be a half adder, so it only takes two inputs, and then the carry generated by the first input, the first half adder is going to be the carry in for the second full adder, and then serially there are going to be 15 full adders. So let's check out the code. Let's run it. We have some test cases over here, so the test cases will be generated in output and we'll get the output. So for these test cases, for A and B, we get the added output. So this is the correct output. We can compare it with the expected output and it is the same. So let's get on to 16-bit incrementer. So the incrementer and adder are both the same, but the only difference lies in the first bit. One of the first bit is going to be true. So what we are going to do is, if there is a number A of 16 bits, we are going to add 1 to it. We are going to increment it by 1. So the first bit of the B is going to be 1 and other bits are going to be 0. The first bit, like the first in the sense from last, first from the last. So the last bit is going to be 1 and all the other things are going to be 0. So the 1 will get added to the input, and the input is going to be incremented by 1 and the output is going to be given out. So let's check out the code for it first. The increment code. There is only one 16-bit adder, and you can, as you can see, there is there is one input. There is one input of 16 bits and one output of 16 bits, and the input is given in the 16-bit adder, and in the output adder only the b of 0 is going to be true and all other is going to be false. So it means that we are going to add 1 to the input variable. So let's run it in the hardware simulator. Let's go to 16, increment 16, increment 16.txt. Now let's run it. Yes. So we can see here 0000 and the output is 0001. So we have incremented the number by 1. And similarly here 00000101 and 00000110. So it is just the same. So finally we come to the arithmetic logical unit. So this arithmetic logical unit is a big chip which can do a lot more than one operation. So here there are a list of operations which what it can do, and also we'll see that code for it. Okay, here we have explained it. So it computes more one of these following functions. It can compute x plus y, where x and y are the inputs. It can compute x and y, x plus y, x minus y minus x, 0, 1. It can give the output has low, output as high, output as minus 1, and it can individually give y, x. So we see that the operation of multiplexer is here. Operation of negation, not operation, and we have increment operation, decrement operation, we have AND operation, OR operation, we have all the bitwise operations and all. So here we can see that there are the input lines, there is x and y input variables, and there are also other variables to denote what kind of operation we are going to do. Like these are like the select lines. So here there is zx, nx, zy, ny, f, no, and all these have a meaning. That is 0, 0 the input. So if you put high in this, it will 0 the x input. If you put high in this, it will negate the x input. If you put high in this, it will 0 the y input. If you put high in this, it will negate the y input. So it works in that way. And there is going to be a 16-bit output also along with ZR and NG. Even these have a meaning, which means if 1, if out is equal to 0, 0 otherwise. And for NG, 1, if out is lesser than 0, 0 otherwise. So the parts include all the logical gates that we created in the past. So it has a 16-bit multiplexer, negation operation. For carrying out the negation operation, we have NOT 16, and we negate one of the input, and we supply that input to the output. So we need a multiplexer to give out that input, right? So we have multiplexers and so multiplexers to give out these y is negated y output, and we have 16-bit AND operation, 16-bit adders, multiplexers, and all those things we use to make the ALU. Now let's try and run the ALU. Now ALU is a very big thing that we have done in 2 projects, and this is the main, like we did the 2 projects just to make this ALU for our computer hack. So let's run it. Okay, so we have set all these, as you can see in the script window. I'll show you after it completes. So we're doing a lot of computations over here. I'll show you. Or else I'll open it here, alu.txt. Yeah, so here we are computing zero, we are computing a low value, we are computing a high value, like we are giving out a high signal, we are giving out a low signal, we are giving out a negative one signal, we are giving out the only the x of the input line, only the y of the input line, we are giving the negation of input lines, we are giving increments of input lines, we are giving the increments of input lines and decrements, and we are going to add both of these things. So for all this computation you can see these select pins, like for computing zero, for giving out the low value we are I'm sorry, for giving out the low value, we are going to set zx as 1, we are going to set nx as 0, we are going to set zy as 1. So what we are doing is, if we set this as 1, then the x will be set as 1. If we set this as 1, then y will be set as 1. And if set this as 1, then we know that uh, here it is given. If you set y as 1, set out x plus y. So since x and y are going to be 1, x plus y is also going to be, x and y are going to be 0. F is x plus y is also going to be 0. So 0 is going to be given out as the output. So in similar way, we compute a lot of computations and we check. So I guess it has done compiling. So let's go and output it. So we have a lot of computations over here. As I mentioned you, there are a lot of computations. It goes up to 377 lines. So all these computations are over here. And let's check the compare. And comparison has been the same. So we know that our ALU is completely working. So this was all about project 1 and 2, and I really thank Abdul Qadir sir for letting me introducing me to this project, because this has opened my mind and brain in so many ways, and I'm really thankful for Dr. Abdul Qadir sir, for giving me this opportunity to get introduced to this NAND2TETRIS project. And thank you, and I'll end my presentation right with this. Thanks a lot. Thank you. This is Korlamudan signing off.